Okay, so this is the second part of this problem, and what we want to find is the stress in that T-beam that is submitted to this distributed load. So just from the first part, what we found is that we found that the moment was max at A and B, and this is minus 25 kilonewton time meter. Okay. What we know is it's a T-beam. So if we look a bit closer to the T-beam, what's happened at the T-beam? This is the beam like this. Okay, let me try to do it straight. Okay, so this is your bar all the way like this. Okay, it looks something like this. And there's a neutral fiber in the middle there. Okay, so this one is, let me try to be, this one is a neutral fiber. And this distance there, this is your Y bar, your centroid that you found with your calculator. What we will need also is, we will need also J of this bar because we have sigma equal minus the moment time Y divided by J, and we need J. So what I propose is like before we start making our calculation, let's find the Y bar and the J with our T-beam calculator. So I'm going there. So it's 20 and 150. So 10, 20 and 150. Okay, and I already changed it, but make sure like this 20, 150, 150, and 20 in my yellow box are updated in your T-beam calculator. And you can go grab the formula, the value of the Y bar is the 117.5 and the value of the J. Okay, so write that on the paper and we grab those two information and we get them there. So 117.5 millimeter and the J 1.66 times 10 at the 7 millimeter fourth. Okay, so we will use those value. Let's make a little drawing to show you what's happening. First, this flexion, this distributed load create a negative flexion all the way in the beam. This is our little grumpy guy, right? So, oops, it's all the way negative. So what's happened is like the fiber on the top, this one, let me try to do some colors. Okay, so what I will do in green there are my fiber that are pulled away, that are in tension. Okay, in my T bar, that will be like this. Okay, tension. Okay, I cut my bar in the middle and it's pulling on it. Those one are in tension. And the Y will be the distance from, so the Y for the tension, only for the tension, that will be the distance. So the total 8 minus the Y bar. So the total 8 there is 170 millimeter. So they will be 170 minus 117.5. That is 52.5 millimeter. Okay, so this is the Y for the tension. And on the bottom, let me draw them in another color. Let's do orange. Orange, doesn't matter. This there, they are pull, like not pull, they are like push, crush in compression on the bottom. Okay, so this one on the bottom, they are crushing that bottom there. And this is even a little bit longer because the distance is a little bit bigger. And so this part is in compression. Oops. And the Y in compression, that will be the 117.5 millimeter. Okay, so those compression are higher than the tension, and all the way to there to 0. Oops, so it's decreasing, and for the tension it's 0 in the center, and after that it's increasing, but there's a little gap there. Okay, so it's decreasing, something like that. Okay, so let's find the sigma now, and you will see how this minus sign is coming in. So sigma for the tension. sigma for the tension equal minus, the moment is negative, minus 25. And the y, so we have the neutral fiber. This yt is positive. So time, just 25 is in kilonewton time meter, so time 10 at the 6 to have in Newton time millimeters. Yt equal the 52.5 and divided by the j that we found 1.66 times 10 at the 7. So we have the sigma in tension that is equal to 79.2 megapascal. Okay, and now the sigma compression equal minus, the minus in the formula, the moment minus 25 times 10 at the 6 to get Newton millimeter, time millimeter, and time the YC that is 117.5, and the YC is down, so the YC is negative. So it's time minus 117.5. It's in millimeter, divided by the J, 1.66 times 10 at the 7. So we get sigma in compression. That is equal to, we have 3 minus, so minus 177.4 MPa. Okay? So what you have to be careful is just like make sure that everything makes sense in the sense so that what we can check. The sigma tension first is positive. We want it positive, it's correct. And also the sigma tension is smaller because it's closer to the neutral fiber. The centroid is up on a T-beam. And for the compression, for the sigma compression, we have a negative sign. We want a negative sign, and also this is larger than the tension because we are more away. This is this one on the bottom, more away than from the neutral fiber. So this bar is the fiber on the bottom feel way more compression stress than they feel of tension stress. For some materials, tension stress and tension like the yield strengths for tension and compression are different. Not for all the materials, it depends. So make sure that you compare them with the correct value. If you have just a sigma normal, you compare that to sigma normal. If you have a sigma for tension and a sigma for compression, you compare them with the sigma tension and sigma compression. So I hope that makes sense. You know now how to use that formula, sigma equal minus the moment times the y, the distance from the neutral fiber divided by j. You know that you can use your T-beam, high beam. We can do any kind of like calculator on Excel, and you understand which one are in compression and what we get as sigma negative and which one is in tension, and I have a sigma positive. Hope that makes sense. Bye-bye.